Hello to everyone. Welcome to our presentation. Today, we'll like to tell you about production use case of embedding-based recommendations. Specifically, we'll be talking about frequency both together recommendation. My name is Ulukbek. I am working as a data scientist at Hepsiburada. My colleague, Selman, is working as a senior data engineer at Hepsiburada. In the first part of our presentation, I will describe you about modeling stage of our project. In the second part of our presentation, my colleague Selman will describe you the general architecture overview. Let me shortly introduce about our company. Hepsiburada is one of the largest e-commerce company in Turkey and in Middle East. It has more than 30 million products and more than 40 categories, ranging from retail foods to electronics. It has high traffic. The number of the visitors per month is around more than 200 million visitors per month. One of the main topics of our presentation is embeddings. An item is represented in a low-dimensional space using embeddings. For example, embeddings represent semantical relation between the words in a sentence by projecting into the low-dimensional space. Why we decided to employ embeddings to generate recommendations? Our old system used co-occurrence-based statistics, specifically Salton H9, which is TF-IDF flight metric. It used behavior data such as product views, add to carts, and orders. It's an item-based recommendation, so users and items cannot be represented in the same space. There are different types of methods to generate embeddings, such as ResNet, Word2Vec, Doc2Vec, BERT, etc. These type of models might be useful in content-based recommendations, where image or text data is used. In addition, embeddings generated from image, text, and behavior data can be concatenated to represent different dimensions of the same item. The main drawback of co-occurrence-based recommendations is that recommendations are not generated if two items do not occur in the same sequence. Also, context information such as neighboring items are not employed. On the other hand, embeddings can be used as features in unsupervised and supervised methods. For example, embeddings can be used in LSTM to model the sequential behavior of customers. In our case, the result embeddings are used in KNN to find the most relevant items. The main goal of frequency both together recommendation is to recommend not alternative but complementary products. One of the main challenges is the diversity of sequences, where products from semantically different categories are included in the sequence. Another issue is related to the scale of recommendations. We are generating recommendations using more than 30 million products distributed over more than 40 categories. We should remember that both together recommendation does not mean that items which occur together are similar. Simple co-occurrence counts are related to first-order co-occurrences, while embeddings is used to calculate the second-order co-occurrences or similarities. In our case, we have employed Word2Vec model. Word2Vec is a simple model. It's easy to train. You don't need any special symbols in training samples. Furthermore, it had a lot of implementations pre-trained for specific business needs. Let's talk on data preparation. User behavior, such as product views, orders in a specific time range, is considered as a sentence. In this case, the set of purchased items correspond to back-of-words model. Let's assume an order included keyboard, computer, and mouse. The corresponding list of items constitutes one observation in a training set. As discussed in the previous slides, sequences contain products from diverse categories. So In order to decrease noise recommendations, sequences are split into subsequences. In the given example, keyboard and mouse are included in the first subsequences, whereas shoes and socks are contained in the second subsequences. Since keyboard and mouse belongs to electronics category, while shoes and socks are items related to shoes. In the given code snippet, context separation using gender and product category information is given. Sequences are grouped into subsequences where products with the same category label and gender information are found in the same sequence. Also, length of the sequence is limited to contain maximum 20 items to support relevancy of recommendations. Let's talk about Vertebral Parameters. Following considerations should be taken into account while training your model. Coverage decreases when mean count is set to lower values. Mean count and network size parameters are set as minimum as possible to increase coverage and to decrease the storage and computational cost respectively. Window parameter is set to the maximum sequence length since orders are random. We use KNN to find the most similar items. Relevancy depends on the selected distance metrics. For instance, Euclidean distance metric measures the distance between 2 points. Cosine similarity measures an angle between two vectors. That's why Euclidean distance affected by vector length. We have used standard evaluation metrics such as precision at K, recall at K, hit rate at K to evaluate our models and to track the performance of the model on the production. It might be difficult to measure accuracy of embeddings. However, standard metrics at least reflect general picture about the performance of the model. We used ML4 to track the parameters and evaluation metrics. It has user-friendly interface to investigate metrics visually and graphically, as shown on the right. Also, it makes easier team collaboration since experiments are stored in central server. Here is a screenshot of ML4 while hyperparameter tuning of the model is shown. The highest precision is depicted with red. Parameters corresponding to the highest precision values are connected with red lines. As shown on the graph, precision achieves the highest values when mean count equals to 5 and negative sampling parameters below 0, and frequent sample parameter is set to minimum value. Here an example of integrating ML4 in the source code is shown. On the 24th line, ML4 is started and parameters are logged on the 30H line. Evaluation metrics are logged inside the function, name it run training function. You can apply arithmetic operations on embeddings. For instance, Adidas and Nike brands can be an average of the product embeddings. Obtained brand embeddings might be used to calculate brand similarities. A few examples of arithmetic operations are given on the slide, but you should remember that accuracy decreases when the categories are represented by the embeddings of low-level entities as product embeddings. Brand similarity is relevant if a brand contains homogeneous products. For instance, if a brand is a shoe brand, then its representation using average of product embeddings might be more accurate compared to the brands which contains products from diverse categories, which is shown on the right. Thank you for your attention. we have discussed the modeling part of our project. Now my colleague Selman will describe you the general architecture overview of our project. Please, Selman, take your time.
Thank you, Lupek. Now I will give information about the general view of the architecture and production phases of the model. We need a system that makes it possible to train a new model, evaluate it with offline metrics, experience it with a user interface. So we started designing this system shown in the slide. The system has two major phases, experimental phase and production phase. After making all the measurements, if the modeling and indexing results are successful, we can put the model to the production system and monitor it with the online metrics easily. The system that we will design and implement should give in continuous delivery ability to the recommendation team. Continuous development and deployment ability is very crucial when you create a system that needs incremental improvements. In the slide, you can see the experimental phase on the left that starts with data preparation with content-aware manner. After that training model, measurement of the offline metrics process and metadata generation comes. Metadata includes category hierarchy, gender, price, and brand. These metadata information are used by post-filtering actions. After creating an embedding model and creating a product embeddings with this model, then it comes to KNN indexing. Indexing phase is when the HNSW library comes to the scene. We create a KNN index tree with embedding data and with metadata. A binary file is generated from this indexing process. KNN indexer puts the binary file to a file storage with a test label if all offline metrics of model training and index creation are satisfying. After index creation, we are ready to start an API with the index binary that was created by KNN indexer. API application can query recommendations very fast on the generated index. When API starts, it gets the final binary file with matching label from binary file storage. But we can try and see the recommendation results with experimental UI at this phase and decide the post-filtering parameters. If the experimental check is also okay, then we just change the direction of deployment to the production and make the model results available to customers of hepsiburada.com. After productionizing the model, we always track the online metrics via superset, which uses Apache Hive as the data source. Daily and weekly online metrics controls are very important. We may create enhancement tasks using these metrics. These enhancements could be done in model training, index creation, and post-filtering parts of the system. While creating this system and data pipeline, we need to make some tricks. I'm going to mention them briefly and show some code samples. After model training, we need to create embeddings of all products. That means processing millions of them. Creation of embeddings on a single machine takes many hours to finish. To overcome this time consumption issue, we use PySpark Pandas UDF. Thanks to Pandas UDF, we could parallelize the embedding process using our existing Hadoop cluster's power. It takes less than 1/50 of the single machine's time consumption. If you need to use two pandas function of Spark data frame, be careful. This conversion consumes more memory than expected. You can see the code sample for the pandas UDF scenario that I mentioned. Embedding creation is done in UDF with a distributed approach at line 28. Code creates random group ID for all records to distribute them over this group ID at line 42. At line 45, create embedding function is applied to the data frame using GRP column as a grouper value. So if your group count is 50 and you have 500,000 product records to create embeddings, then every node of the cluster processes only approximately 10,000 records, and every node does this job in parallel. After the executor's jobs are done, all the embedding data will be union in the driver node. Then you can do other processing on it. In our case, the next process is writing it to the HDFS. For measuring the model quality, there are three important examination components. Offline metrics are measured at the training time of the model and the indexing time of the embeddings. Experimental UI provides examination with the human eye and makes it possible to decide about the filtering parameters. Online metrics are measured after the production phase to see the real effect of the work done. We use nearest neighbor algorithm to create KNN index. Thanks to this KNN index, we can query over it and generate recommendations. Before deciding the library for the nearest neighbor algorithm, we checked ANN benchmarks. There is a graph on the right where you can see a performance overview of the libraries. For details, you can visit annbenchmarks.com. After that, we decided on programming language and choose Golang for both indexing and serving layers because of Golang's small deployable executable binary and lightweight subroutine mechanism. Other than these, we checked similarity function possibilities different from Euclidean distance, and if we needed a distributed index or not. If your case makes it hard to create index from scratch, then use a library that makes it possible to incremental item insertion or deletion. In our case, it's not a necessity. We decided to go with HNSW library, Golang, and custom developed post-filtering layer. There are trade-offs for the decisions made over parameters of building the nearest neighbor tree with HNSW library. If you decide to keep the tree simple and lower the neighbor count, it results with less resource consumption, but poor recall value. If you increase the tree's complexity, you will get higher recall values, but be careful about total resource consumption. It will become a waste of time and resource after a point. You need to choose optimal values for indexing parameters. The fact that the embedding vectors of the products are close to each other in the vector space doesn't require these products to be shown to each other as a recommendation in all cases. In many cases, a post-filtering of the recommendation product list is required. In this way, recommendations that may seem unrelated from the point of view, brand, price, gender, and category can be eliminated. Also, these two brands cannot be shown with each other or do not show adult products with health products type business requirements necessitate the post-filtering. Creating KNN index with post metadata included enables us to apply any kind of post-filtering. Now we can see three examples of simple filtering functions that we implemented in our serving layer. If your recommendation context is clothing, then you may want to recommend products with same gender meta info. Or if you are recommending an electronic device to another one, then recommending a $10,000 device for a $100 headphone may not be a good idea. Using these metadata while training the model is another way to handle this situation, but it causes more complex training process and also doesn't guarantee the results as in the post-filtering process. While deciding the parameters of post-filtering, you need an evaluation medium. We implemented an experimental UI for this purpose. With the try-fail method, we can decide the parameters like category, price, brand, gender, etc. to gather the best results from the model. And we can do it by seeing. After decisions made by the team, we can use the decided parameters in the implementation of serving post-processing layer. Performance metrics of the serving layer are very important for us because we are serving millions of customers as the recommendation team of hepsibrother.com. So our serving layer has to handle large scale of traffic with low latency. For being sure about performance quality of our serving layer, we applied load test to our API application. For a single instance of API application, you can see the graph screenshot taken from the Grafana dashboard. Single instance of application can give responses up to 8K requests per second under 1 millisecond response time. Here, two examples of frequently bought together recommendations from our production system. On the left, for a laptop computer, there are computer accessory products recommended. On the right, for a camping tent, other complementary camping equipment are recommended. Best way to understand the real success of or fail of a recommendation model is performing it on the production, gathering clickstream and order data and analyzing them under the well-known headings, which are conversion-related metrics, coverage-related metrics, and order revenue related metrics. These metrics can be grouped in terms of different dimensions such as placement title, channel, and gender. Using only CR/CTR is not enough. Try to see the big picture with other metrics. Be careful about popular products and category context. Good CR value for one category may not be good enough for another one. Separation of context using the right dimensions gives you better inference. As final words, we have suggestions for you. Using embedding representations in recommendation domain is a good and working method. Word-to-vec training is a simple job, but tuning the parameters wisely is important. Using offline performance metrics are also crucial to get best from the model. Application of arithmetic operations may not work as expected. It's more complicated than king minus man plus woman equals to queen equation. Be careful when using it. Using agile methodology while developing such a system provides seeing the dead ends and successful results as early as it can. Giving up the dead end and experiment and putting the effort on the most promising experiment buys you time. Scale is the #1 question while designing this serving layer. Experimental UI is a good way of evaluation of a model and good medium for deciding the post-filtering parameters. And finally, never-ending process. Keep tracking the online metrics. Thank you all for listening us. Please ask any questions you want. We will be in Q&A chat room. We wish everyone a good summit.